The next question of CODECHEF starters 118 is count substrings. So in this question, we are given with an initial string S0. So this is some string of length n. Now we can deduce new string from the previous string. That is, let's say if we know what is I minus 1th string, then ith string is deduced as follows, as per the question. S of I is equal to S of I minus 1, the normal string, that is the previous string, plus the concatenation of the reverse of the previous string. Right? So this is how ith string is deduced. So similarly, it is like to deduce ith string, if the previous I minus 1 string is deduced, then it's S of I minus 1, concatenation of the reverse of the S of I minus 1. So from S0, S1 is computed as S0 plus reverse of S0. Similarly, S2 is computed as S1 plus reverse of S1. So on, till for any I, Si is computed as Si minus 1 plus reverse of Si minus 1. This is what is mentioned. Now we need to find out in S of k, in the string S of k, how many substrings are there which are equal to S of 0 in string S of k. How many substrings are there which are equal to S of 0? So this count can be very large. So we are given with 10 power 9 plus 7. So we need to output it modulo 10 power 9 plus 7. Now if we look at the constraints, test cases can be in the range 1 to 10 power 5. N is in the range 1 to 10 power 6. And K is in the range 1 to 10 power 9. And it is also guaranteed that S of 0 will only consist of lowercase characters, and summation of n over all test cases won't exceed 2 into 10 power 6 as mentioned. So let's see how we can solve this problem. So to solve this problem, firstly, the prerequisite is you have to know at least one string matching algorithm, string pattern matching. Algorithm. So you should either know KMP algorithm or Z function or string hashing. So you have to know this. So now we'll be using Z function and solving this. So instead of Z function, you can even use KMP or string hashing to for the same purpose for which we'll be using Z function now. So here, initially we are starting with S of 0, right? That is the initial string. And now what we do is in S of 1, we put S of 0 plus reverse of S of 0. Now my claim is firstly, the first observation here is if S of 0 is palindrome, then it's well and good. Otherwise, if in case S of 0 is not palindrome, then when can we see a palindrome? If S of 0 is not a palindrome, then for sure, for any string, like if S of 0 is not a palindrome, for sure, no matter what S of 0 is, S of 1 will be a palindrome. That is because we are adding S of 0 plus reverse of S of 0. So for sure, for any string, this will hold. S of 1 will be a palindrome. So now this observation is sufficient enough to solve the problem. So now we know that for any string, S of 1 will be a palindrome. So let's calculate in S of 1 how many substrings are there, how many substrings are there which are equal to S of 0. Now, once we know this, let that count be C1. Now, when we are calculating the value for S2, then it is about, now what we'll be doing is we are adding S1 once plus again a S1, right? Why? Because we can observe that this is a palindrome. S1 is a palindrome, so reverse will also be the same as S1. So we are adding S1 once and again S1. So number of substrings which are there, which are equal to S of 0 and S1 are C1. So when we add these two, it will be C1 plus C1. As we are taking it twice, we can say it is C1 plus C1 plus we'll get some extra factor. So we'll get some extra value. And let's see why do we get this value. So let us consider a case. If our string S0 is DCC, DDCCD, let's say. Now in S1, if we observe, we get DDCCD, right? So now here, if we observe, this is one substring which is equal to S0, and when we concatenated S plus the reverse of S, we can see that some part of the first S0 and some part of the second of the reverse of S0 merging together formed one substring which is equal to S0, right? So now our aim is to calculate when we concatenate, there can exist two scenarios only. That is, one scenario is if we concatenate S0 plus reverse of S0, and one more scenario is if we concatenate reverse of any S, so let's not call it as S0, Si and any Si, reverse of Si plus Si, right? So these are the two scenarios that can exist only, right? And now we know one more thing, that is if I is greater than 1, these two are same, right? If I is greater than 1, then reverse of Si is nothing but I, and this is also I. So both the scenarios are the same. But if I is less than or equal to 1, then we'll have two scenarios. So here itself we can write that. So if I is greater than 1, then reverse of Si is equal to Si. If I is less than or equal to 1, then it won't hold true, right? So now we have two scenarios here. Now our aim is to find out, after merging Si plus reverse of Si, what is the value that is contributed. Similarly, after merging reverse of Si plus Si, what is the value that will be contributing, right? So in this merge, how many S0 substrings will get created? Similarly, at this particular merge, how many S0 substrings will get created, right? If we know these two scenarios, number of substrings, then we can find out what is the value, how many substrings are there for S of k, right? We can formulate it and find out how many substrings are there in S of k, which are equal to S0. So now let's see how we can do that. Firstly, our aim is to find out only for S0, there exist two cases, right? So for S0, the two scenarios are, so first scenario is we need to find out after merging S0 plus reverse of S0, how many S0s are present. So for that, what we can do is, uh, so here you should know, you should have idea about Z function. So in case if you are not clear with, if you are not, if you don't know Z function, then first go refer what is Z function and then come back and watch the video from this point. Or if you don't know Z function, you should at least know KMP or Z or string hashing. So here, what we'll be doing is, this is our concatenated part. In this part, we are just finding out how many times is S0 coming as a substring. Right? Number of times S0 is coming as a substring in S0 plus reverse of S0, this string. That is because initially we put S0 and reverse of S0, right? So number of times, let the number of times up S0 appearing be C1, and similarly the reverse case, number of times will S0 appear in the concatenation of reverse of S0 plus S0. Let that be C2, right? Now, we can observe that basically why we are doing this is, let me take some small example. Let our string be S. Then here, for the first time that we concatenate, what we are doing is we concatenate code and E D O C. So this is nothing but S0, reverse of S0. So in this string, we need to know how many times did S0 come as a substring. Now, from here onwards, we know that S1 will become a palindrome, right? So from here onwards, no matter which case we take, it will always be as follows. That is, the last part will be reverse of S0 whenever we are adding uh, Si minus 1 plus reverse of S minus 1. Always it looks like Si minus 1. It looks like always will keep merging reverse of S0 plus S0, because we don't care about this part. Why? Because S0's length itself is equal to the reversed part of S0. So this won't come into the picture while we are counting the subsequences, while we are counting the substrings which are equal to S0. So now if we see here, now we'll be adding So from here onwards, initially we did S0. Basically, initially, when we are merging, it was S0 plus reverse of S0. But after the point S1, because S1 will turn out to be a palindrome, like the string will turn out to be a palindrome from point S1. So from here, always whenever we replicate Si minus 1 plus reverse of Si minus 1, we'll keep merging S reverse of S0 and S0. And if we look over the next case also, it just looks like 4. And here we put C and so on. So if we see, this is nothing but reverse of S0 and this is S0. So we only need how many substrings are formed due to merging this part, right? Because we already know the answer for this whole string and the next whole part, right? We already know the answer for that. Similarly, if we look over S2, we already know the following answer. That is, we are just concatenating S1 and reverse of S1. And we know reverse of S1 is just S1, as S1 became a palindrome. So this is S1. We can just add up answer of S1, answer of S1 plus the merge value. Let us call this as merge value. After, due to merging, what is the value that we got? So for every state, this is what gets added up. And the value that we get is nothing but C2, right? So now let's see from this. So only for the first case, we need to know how many S0s are there after merging. Yeah, how many S0s got created after merging S0 plus reverse of S0. So this will tell us the initial value, that is value of S1. So C1 has in S1 how many S0 are there as a substring. Now, initially we know till S1 we know what is the answer. Till S1 answer is C1 and C1 is just find out how many substrings are there in S0 plus reverse of S0 which are equal to S0. Right? Now, we know that from S1 onwards, merge will happen on reverse of S0 plus S0, just like how we saw now. So now the merge value, we can pre-calculate that merge value. So the merge value is C2. So to calculate that, you can just add S0 plus hash plus reverse of S0 plus S0 and then use Z algorithm or KMP. This is a separator. So we can use a string matching algorithm to find out how many S0s are there as a substring in this string. Right? So now we know C2 is that value. So C1 is the value of string S1, but now we want only the merge value, right? We only want the merge value, not the complete value. So merge value in the sense some part should be from this and some part should be from this. A part which is completely from this, we don't want. A part which is completely from this, we don't want, right? So that merge value is nothing but C2, but we can't say it is C2 only, because in C2 we even include one value which is completely in one part only. And in case if S of 0 itself is a palindrome, then we include two such values, right? So now what we can do is, if S is not palindrome, then we can just subtract C2 by 1, because we just saw we want the merged value, that is some part should be from reverse of S0 and some part should be from S0. Else if it is a palindrome, then we need to subtract two things. Why? Because it is a palindrome. So if it is not a palindrome, we know that its reverse part is not equal to the current part. So we only count one value which will completely belong to reverse of S0 or S0. And sorry, we'll only count one value which completely belongs to S0, not reverse of S0. And in the case of a palindrome, reverse of S0 will be equal to S0. So one part will completely lie in the left and one part will completely lie in the right. So to remove those things, uh, these these subtracted values, they are not contributing they are not counted due to merge. They are counted due to they are not counted due to merge. They are just counted because the value is completely present in the right part or completely present in left and right. Right. So that's why we ignore all those which don't all the values which don't come up due to merge of reverse of S0 plus S0. So now we know the coefficients C1 and C2. Now let's see how we can compute the value. For string 1, we know that value is C1 and we just saw how to compute it. Just call just perform string matching on this and count how many S0s are there in this string. And we saw how to count C2. So how many S0s are there in this string. So this is the pattern, this is the main string. Now let that be C2. Now if S0 is not a palindrome, we know that one value is completely lying in the right, so we remove it by 1. We remove 1 from it. If it's a palindrome, then we remove 2, because one value will lie completely in the left part and one in the right part. Now when we are calculating S2, we know that S1 became palindrome, which is the main observation that we made and which was sufficient. So now in S2, we can say that we are adding S1 plus S1. That is nothing but we are adding C1 plus C1 plus we'll be adding C2, the merge value. So if we look over this, it just looks like, to find out this, we do 2 into C1 plus C2, right? Because in S1, number of S0s are there which are as a substring. In this S1, number of substrings are there which are as a number of substrings which are there which are equal to S0. So 2 into C1, 2 into such count plus C2 is the count is the number of substrings that got formed due to merging these two things. That is due to some part uh, due to due to the substring which is equal to S0 and which is formed by some part of left and some part of right value. Okay? So if we look over, this is reverse of S1 and this is equal to S1, right? Because it's a palindrome. So that's why I replaced it with S1. So now if we see for S3, it is just S2 plus S2. That means we multiply the value by 2 into the previous value, that is 2 into C1 plus C2 plus the merge value, right? After S1, the merge value will continuously keep being C2 only, which we proved. So now we are at S4. We do S3 plus S3. So this becomes 2 into C1 plus C2 plus C2 plus C2. Right? So now if we just expand this, we can observe that if we just simplify this, it just becomes 2 into C1 plus C2. This becomes 2 square into C1 plus 2 into C2 plus C2, and then it further becomes 2 cube into C1 plus 2 square into C2 plus 2 into C2 plus C2. Okay? So this is how the pattern is once we simplify. So this is still S4, right? This is for S4. So now from this we can say that for S of k, the value is 2 power k into C1. The value is 2 power k minus 1, not k. 2 power k minus 1 into C1 plus C2 plus 2 power k minus 2 into C2 plus 2 power k minus 3 into C3 into C2 plus so on plus 2 power 0 into C2. Right? So only the first value is C1, rest all it's the second coefficient. So now if we bring it down, if we break it down, it just becomes 2 power k minus 1 into C1 plus C2 into 2 power k minus 2 plus 2 power k minus 3 plus so on plus 2 power z. Right? So if we apply geometric progression on this GP, we can observe that here if we see the ratio R is 2. So now S of k is nothing but, for S of k, the value is nothing but 2 power into C1 plus C2 into 2 power k minus 1 minus 1. Right? So this is what we get if we apply. That is because we can write this part as a r power n minus 1 by r minus 1, right? So here n is nothing but 2 power k. Here there are n terms. So here n is k minus 1 because there are k minus 1 terms, 0, 1, 2, so on till k minus 2. So 2 power k minus 1 minus 1 by 2 minus 1. So here r, the ratio is 2. Factor r is 2. So now we just reduced it to a simple thing. Now it is about, now just calculate. Now we found out C1 and C2. So just calculate what is 2 power k minus 1 into C1 plus C2 into 2 power k minus 1 minus 1. What is this value? And ensure that this value can be very large. So ensure that you calculate this value performing modulo with 10 power 9 plus 7. So this way you can solve the problem. So now if we look at the time complexity of this, here to find C1, we'll be doing basically our pattern length, like S of 0 can be 10 power 6 length in the worst case. So assuming n is the length of this, then when we concatenate two things, that is S0 and reverse of S0, it becomes 2 into n. So performing KMP or Z algorithm costs us n plus m, where m is the pattern length and n is the length of the string. So here the length of the original string is 2 into n and length of the pattern is n. So we can say it is big O of 3 into n for the first scenario. That is to calculate, this is to calculate C1, plus to calculate C2 we need 3 into n. Now once we calculate C1 and C2, it is just finding out what is 2 power, it is just finding out the value from this derived formula, right? So here to find out 2 power we can use modulo, we can use exponentiation, binary exponentiation, modulo with binary exponentiation. So plus it will cost us log 2 of k. So this is the perfect practical time. In terms of big O notation, we can say it is big O of n plus log 2 of k, log base 2 of k. So I just rounded off k minus 1 to k and return it. I have written it as big O of n plus log base 2 of k. So practically this should be k minus 1 because we are computing 2 power k minus 1 time. So let's ignore that minus 1. So it's equivalent to big O of n plus log base 2 of k. And if we look at the space complexity, it depends on how you implement. So here, assuming we are using z function, and z function takes a z array of size length of the string plus the pattern. So we can say space over here is 3 into n for C1 plus 3 into n. This is to calculate C2. So it is big of, so we can say it is equivalent to big of n. So all this is per test case. And here it is guaranteed that summation of n, sum of n over all test cases won't exceed 2 into 10 power 6. So yeah, so it is 2 into 10 power 6. So we can assume that the worst case can be test. There are two test cases with n perfectly equal to 10 power 6. And this time complexity and space complexity is sufficient enough to, considering the constraints, time complexity and space complexity, it is sufficient enough to pass in 1 second of TL with the given memory limit. So this way we can solve the problem.